In this talk, I'm going to talk about a new modulation format that was proposed by my group called mode vector modulation. And in particular, I'm going to talk about the optimal signal sets. I would like to acknowledge here the contribution of my co-workers, Eric Finke and Jarek Wapis. This format is an extension of Stokes vector modulation and is intended for multi-core or multi-mode fibers, or we can have free space links where we use multiple modes, or even we can do a time domain implementation. So we know that currently for the distances less than 10 kilometers, direct detection receivers are used. And in the last decade or so, there were a flurry of designs for direct detection receivers used for advanced modulation formats. One interesting thing was going back to polarimetric receivers and using modulation formats with them simply because they are self-homodyning receivers. So Stokes vector modulation is a rediscovery of the old polarization modulation, polarization shift keying, and it is really a family of modulation formats that can be used together with polarimetric receivers that now are called Stokes vector receivers. So what is the advantage of Stokes vector modulation? Basically, if we compare it to MRE-PAM, well, MRE-PAM is a one-dimensional format, and its energy scales quadratically with the number of points that we have in our constellation. However, Stokes vector modulation, for example, polarization shift keying, which is a special version of equi-energetic Stokes vector modulation signals, scales linearly with the number of constellation points. And this is the motivation for our work, because if we go to a multi-dimensional Stokes space, we can have a more gracious scaling with the number of constellation points. So higher dimensionality means higher energy efficiency. In this talk, I'm going to discuss about the basics of mode vector modulation for those of you who haven't seen any of my previous talks. Then I'm going to discuss about the main topic, which is constellation design. And finally, I'm going to discuss about the performance evaluation of mode vector modulation formats and their comparison to conventional modulation formats. I move now to the introduction, which is taken by the number of previous presentations and the paper that we're planning to submit to JLT. Mode vector modulation consists in sending pulses over all spatial and polarization degrees of freedom. Here I show an implementation for a homogeneous multi-core fiber with ideal, identical single-mode cores. So we have 4 degrees of freedom, we have 2 polarizations per core, and we launch the same pulse, but with different amplitudes and initial phases. And these are the parameters that characterize the modulation format. Now, this example might not be the best. In reality, we want complete degeneracy of all the degrees of freedom, similar to polarization mode dispersion. So we accumulate, similar to the case of single mode fibers, so we accumulate minimal polarization mode dispersion. In general, we can generalize the scheme that I show here. In the case of K cores, we have 2 polarizations per core, so we have n polarization and spatial degrees of freedom. And the difference compared to space division multiplexing is that here we don't use the modes independently, but all together as a single channel to create energy efficient spatial modulations. But as I said, we can take into account the equivalency between spatial modes and time slots and make a multi-dimensional format in time domain using exactly the same mathematics. At the receiver side now, for Stokes vector modulation, there were recent publications that proposed to replace parts of the polarimetric receiver with 90-degree hybrids and photodiodes that either measure the real and the imaginary part of 2 incoming signals, or they measure their power. So we'll use this as a unit cell for the mode vector modulation receiver, and we can concatenate n-1 of these unit cells, where n is the dimensionality of the zone space. And we can use DSP in order to be able to detect the Stokes symbol and also derotate possible rotations that happen inside the multi-mode or multi-core fiber. A centerpiece of this work was the calculation of the symbol error probability. And I'm going to show you why it is difficult. So in the 3D Stokes space, here you see 64 points, approximately equally spaced on the Poincare sphere. And if we assume that the different symbols are equiprobable, we can use the maximum likelihood criterion for incoherent detection in order to plot the correct decision regions that are shown here as irregular polygons. In order to calculate an accurate closed form expression for the symbol error probability, you have to take into account these irregular boundaries. This can be done only for very small constellations, and certainly it is very hard to generalize to higher dimensional Stokes spaces. So one way to avoid the exact calculation is to use a bounding technique. And we use the union bound, where you consider pairs of points. Let's assume here you are sending this symbol, which is denoted by S sub m in Stokes space. And you consider the probability of getting a different symbol Sm prime. So the idea is that the amplifier noise can make our correct symbol go to the wrong hemisphere. This union bound was used initially by Betty in a paper about polarization shifting in the 90s. Then Benedetto and collaborators improved this calculation, but this all was for 3D Stokes space. And more recently, Kikuchi published papers on this. However, for the n-dimensional zone space, the calculation becomes very complicated, and I would like to give credit here to my coworker, Jarek Wabis, who derived this formula from scratch. If we see the bound, it depends on the pairwise error probability, which itself depends on the Markov function of the first order and the modified Bessel function of zero order. And inside the arguments, we have the symbol signal to noise ratio, and we have also the multiplication of two symbols in the Stokes space or equivalently in the zone space. This parameter gamma here is known to mathematicians, and it is called the Fubini's 2D metric. So apparently this quantity here is going to affect our error probability. I move now to the constellation design. The formula that I showed you before is useful to do rapid calculations, but it is not so fast in order to use it as an objective function in order to optimize your constellation. So we resorted to a physical analog where we assumed that our constellation points are same charges on the surface of a conductive hypersphere, and this represents the Poincaré hypersphere in the higher dimensional Stokes space. We assume a random configuration of same charges in the beginning, and then we allow Coulomb forces to push the charges around until they achieve an equilibrium. So the electrostatic potential energy for a configuration of m charges is shown here. And as you can see, it depends on the pairwise Euclidean distance in Stokes space. But due to the properties between zones and Stokes spaces in the generalized case, we have this identity here, and this allows us to write a recursion and use the method of steepest descent in order to update the configuration of charges again and again until we reach equilibrium. Now, this method about solving this problem, which is called the generalized Thomson problem, was used by mathematicians both in the two-dimensional zone space and in the general case of an n-dimensional zone space, and I list some references here. Here you see some example results for the two-core multi-core fiber. We have 4 spatial and polarization degrees of freedom, and I show you 2D projections of the optimal constellations with 16 points and 256 points. Okay, how about B2 symbol mapping? Well, the problem is that gray coding is not possible, but we can use simulated annealing and label the vertices and move the different labels around until we minimize a certain objective function. And for this, we used the actual error probability. Here is an example for the case of a 2-dimensional zone space, 3-dimensional Stokes space, and 8 constellation points. The optimum configuration of 8 constellation points is the square anti-prism. This was calculated by Benedetto and collaborators in the early 90s. Okay, here is the B2 symbol mapping that one can calculate by hand in this case, but we tested simulated annealing. It found the right labeling, and we trust that the results that I'm going to show you now are pretty well optimized. Notice that I'm not talking about true optima. This is numerical optimization, so nobody knows if these are the true global optima, but definitely they're optimized constellations. So this is now the third part of my talk, and this is the main result. Here you see spectral efficiency versus bit SNR per spatial degree of freedom plots. The different colored curves are different cases of zone spaces from n equal 2 to n equal 8. Points on each curve represent different constellation cardinalities. And the important thing to notice here is that as we go to higher dimensional Stokes space for n equal 4, n equal 8, which correspond to 2-core multicore and 4-core multicore, you get C-shaped curves, and the apex of each curve is a simplex constellation. And we have calculated the slope of these curves using asymptotic analysis in the paper. I'm not going to talk about that. Here you see how the mode vector simplex constellations compare to other coherent and non-coherent formats. The important thing to keep in mind is that we get a significant sensitivity improvement compared to Stokes vector modulation, but at the expense of spectral efficiency. As you see, the blue curve goes downwards as we increase the dimensionality of zone space and hardware complexity. One last note, simplex constellations are calculated by mathematicians, so you don't need to do this numerical optimization if you want to use simplex constellations. You can use these vectors here. They're published on a web page, and they go up to dimensionalities of zone space of 150. To conclude, our group introduced a new modulation format called mode vector modulation. It is amenable to direct detection, and it is an extension of Stokes vector modulation to multi-mode or multi-core fibers or free space modes. We computed optimal signal sets, and we optimized the B2 mapping, and we showed that simplex constellations give the best trade-off between spectral and energy efficiency. One takeaway message is that MVM is superior to conventional modulation formats in terms of energy efficiency due to the higher dimensionality of signal space. I would like to acknowledge the contribution of our sponsors, and I would like to thank you for your attention.